So, good morning, everybody. Welcome to the last edition of the Pangolin Seminar before the summer recess, that is to say the Christmas recess. Today, it's my great pleasure to welcome Ben Lowe from Princeton University, who will be speaking to us about minimal surfaces in negatively curved free manifolds and dynamics. So, it's over to you, Ben. Oops, you're on mute, Ben.
Great, yeah.
Right,
Thanks.
okay.
I'll just share my iPad screen real quick.
Mm-hmm.
I think you have to make my iPad
Oh,
co-host.
goodness, I forgot to do that. Now you can share. Silly me.
Yeah, share my screen. And as I'm doing that, I also put a link to my slides in the chat.
That's correct. And I will upload your slides. Give me a second so that you've got the slides there. Okay, great.
I just put them, yeah.
Right.
Cool. So, yeah, if anyone wants to page back as I'm going through my talk, then you can just do that. The link there. Cool. So everyone can see everything okay and hear me okay?
Yep.
Hopefully.
Yep.
Yeah.
Awesome. So yeah, guess get started. And feel free to interrupt at any time. Questions are very welcome. But yeah, so I'm going to be talking about minimal surfaces and negatively curved three manifolds of dynamics. So yeah, I guess what this talk is sort of about is, so for geodesics, they have kind of a like metric variational aspect, like they locally minimize length. But they also have a dynamical aspect. They're like orbits of the geodesic flow, and there's kind of a like rich interplay between these two different sides, like what a geodesic is. And I guess geodesics are one-dimensional minimal surfaces. So if you look at minimal surfaces in higher dimensions, they're like definitely much more variational objects. But I guess this talk is going to sort of be about how looking at minimal surfaces from a dynamical perspective can also be fruitful and interesting in kind of a very special restricted setting. But yeah, so I'll get into it. So, right, so we're just start out with throughout this talk, M is going to be a closed hyperbolic three manifold. So yeah, just a quotient of three-dimensional hyperbolic space by just a co-compact or discrete co-compact group of isometries. And kind of one of the main objects for this talk is the Grassmann bundle of tangent two planes over M. And so what this bundle is, it's just for each point, you have the tangent space to M at that point, and you can look at all the tangent planes in the tangent space that pass through the origin. So just, GR2 of R3, the Grassmannian bundle, or the Grassmannian of just two-dimensional planes and three space. And so that's like the fiber over each point for this bundle. So at each point you just have all of the tangent two planes in the tangent space at that point that go through the origin. And that's a bundle. And in the case here where M is a closed hyperbolic three manifold, this bundle is going to come with a natural foliation, which we'll call blue F, by tangential lifts of immersed totally geodesic planes. Okay, so how does that come about? So for each point in GR2M, so it's for each tangent two plane in the tangent space to M at some point. What we can do is we can just take the kind of plane in the tangent space that corresponds to that element of GR2M, and take the image of that tangent plane under the exponential map. Okay, and so that'll give us some immersed totally geodesic plane inside M. Like probably in general, it's going to be intersecting itself horribly, but what you can do is you can lift it to this GR twin bundle by just at each point taking its tangent 2 plane at that point. And this will, you can check that this will give you a foliation of this Grassman bundle of tangent 2 planes. Yeah, so this foliation blue F is going to be sort of the model case for the main theorem of this talk, and so it's going to kind of come up again and again. So yeah. Right, so this theorem that's due to Ratner and Shah independently, you follow some Ratner's theorems, but Shah also gave a proof, is that every leaf of this foliation blue F is kind of complete rigidity that holds here, where either it will close up to be a properly immersed, like totally geodesic surface inside M. And if it doesn't do that, then it actually has to be dense inside the Grassman bundle of tangent 2 planes. Right, so a couple comments on this. So first, another way to say this theorem, if you haven't quite internalized what this foliation blue F is yet, is M, it's the universal cover of M is hyperbolic free space, right? So what this theorem is saying is if you take a 2-dimensional totally geodesic plane just upstairs in 3-dimensional hyperbolic space, the universal cover of M, and if you project it down to M, then either it will close up to just like a proper surface, or else it'll go everywhere. Okay. Right, and so the reason, so really this theorem is sort of a kind of the leaves of blue F are really kind of corresponding to like SL2R orbits for the action of SL2R on the frame bundle of M, right? Where it's the isometry group of 3-dimensional hyperbolic space is just PSL2C, and so really kind of what we're looking at like for like how what these leaves are doing is like how these like SL2R orbits are behaving, and that's kind of where like Ratner's theorems come in, where like the fact that SL2R is generated by unipotent subgroups, so just upper triangular subgroups basically, with ones in the diagonal, is gonna let you apply Ratner's theorem, and you get kind of this really like strong rigidity here. And what I'll say also is that this is like in complete contrast to what happens for, if you look at 1-dimensional totally geodesic like subspaces of hyperbolic manifolds, like if you look at geodesics, then orbits for the geodesic flow can be like pretty much do anything. So
Ben, so Samuel here is asking whether the construction of the foliation F holds for any complete Riemannian manifold.
That's a good point. You need hyperbolic, or for what I'm saying, in order for the leaves to be totally geodesic at least. I guess if you did this for like a general negatively curved metric where you just tried to shoot out, you just took the exponential images of planes, then you would get surfaces inside your manifold, but they wouldn't be totally geodesic in general. But yeah, I guess you could do kind of some of this for any Riemannian manifold. And I guess for other symmetric spaces too, like I'm not really using dimension 3 here. And also, you could also do kind of similar things. But yeah, thanks for asking that. So we'll just say about this kind of Ratner-Shah theorem that, I guess based on, it's maybe a little bit surprising based on what happens for geodesic flow where the orbit closures are terrible, but kind of the fact that, kind of Ratner's theorems kind of come in here, puts a lot more rigidity on what can happen. All right. Cool. So now I want to talk about this theorem that Caligari, Marquez, and Neves proved. And to do that, I'm going to kind of take the next 2 pages or so to say some definitions and some of the setup. But yeah, I guess their theorem is sort of the starting point for my work. So I'm going to just kind of explain that briefly. Right. So follows from work that Conor Markovich did in a series of papers that the fundamental group of our closed hyperbolic three-manifold M contains lots of surface subgroups or subgroups that are isomorphic to the fundamental group of a closed surface. Okay. There's like very beautiful proof of this. Uses kind of mixing properties for the frame flow to get this like purely kind of group theoretic fact about the fundamental group of M. And yeah, these surface subgroups are going to be an important object for this talk. Minimal surfaces, and maybe you don't have to say too much about what that is in this seminar, what those are in the seminar, but I mean, basically they're going to locally minimize area in the same way that geodesics locally minimize length, which you can also express by saying that they have everywhere vanishing mean curvature, so they satisfy the second order elliptic PDE, and I guess I would say like in 3 dimensions, like minimal surfaces and 3-dimensional Riemannian manifolds, kind of basic like regularity theory and the kinds of things that can happen are fairly well understood. So that's kind of going to be the setting that we restrict to in this talk. Right, and so to kind of combine the last 2 bullets, what you can say is for each surface subgroup, pi1 of sigma, you can realize it by just like an immersed minimal surface whose fundamental group includes the conjugacy class of the surface subgroup that you started out with. Right, so here kind of we're saying conjugacy class because we don't want to think about base points. And yeah, basically for each surface subgroup that'll sort of the conjugacy class of that surface subgroup will correspond to a homotopy class of just immersions of the surface inside M. And so what you can do is you can minimize area over all of these immersions, and it's kind of a standard thing in the theory of minimal surfaces at this point, due to, I guess, Shane and Yao and Sachs-Lundbeck, that you can realize the infinite area by an immersed minimal surface. And the fundamental group, I mean, yeah, the immersed minimal surface that will realize the surface subgroup or this conjugacy class of surface subgroups. So yeah, I mean, it's just kind of like maybe like a general theorem in geometry geometry where you have, I mean, some like algebraic thing, like in this case, it's like conjugacy class of surface subgroups, and you can realize it by kind of a semi-canonical geometric object. In this case, like this like immersed minimal surface that like minimizes area. Right.
So just to understand the pi1 of the minimal surface, is it isomorphic to the pi1 of sigma or not really?
Yeah, it will be. It will include to well, yeah, I guess there's sort of this issue with base points. So it'll include to the conjugacy class of pi1 of sigma. Will be isomorphic to it, yes, but it won't necessarily be the same one, I guess, depending on which you choose.
Okay, all right, thank you.
Thanks for clarifying that. Right, so the next bullet has some terms which I'll say what they are, but I'll just say it. The limit set of each of these surface subgroups is, it's called like a K quasi-conformal deformation of just the round equator in S2, thought of as the boundary at infinity of 3-dimensional hyperbolic space. Or we kind of summarize all that by saying it's a K quasi-circle. So what's going on with this? So we think of 3-dimensional hyperbolic space as just kind of the Poincaré ball. And so kind of looking at it like that, see like the boundary at infinity is just like the the Riemann sphere, just S2. And what do I mean by the limit set of pi1 of sigma? So one way to say what that is if you just if you take just a immersed surface sigma whose fundamental group includes to pi1 of sigma. So if you just take an immersed surface in M, that's kind of pi1, like injectively includes to pi1 of sigma. And if you lift that to the universal cover to get a properly embedded disk in three-dimensional hyperbolic space, then what the limit set is, like in this Poincare ball model, kind of thinking of it in there, it's the following. So, right, so we have kind of the Poincare ball, which I'm drawing as like a circle here. And then the limit set is just going to be the set of accumulation points of like your lifted surface in the boundary at infinity. Right, so what that's going to look like in this case is it's going to be this Jordan curve in the boundary at infinity, right? So it's going to be this like really kind of squiggly curve. And I mean, in general, it's not going to be like differentiable. It's going to have Hausdorff dimension bigger than 1. It'll be a Jordan curve. And yeah, so it's kind of the image of the equator under these like so-called like K quasi-conformal maps. It's not really important for this talk what K quasi-conformal actually means, except that as K gets closer and closer to 1, that means that like the limit set of this like pi1 of sigma is going to get closer and closer to being a round circle. Okay, so I mean the K quasi-conformal here is just sort of controlling.
So just a second, Ben. I see that Jeremy has a question for you.
Sure.
Yeah. You get a control on the K of the K quasi-conformal map?
Yeah, that's a good point. That's kind of going to be the next thing that comes up. But yeah, so the Kahn Markovich, they actually in their things, in their work, they actually kind of produce like a lot of these for K small even.
I see.
Yeah.
Okay. Okay, thank you.
Yep. Cool. So yes. So basically, I mean, we have these surface subgroups, and then we kind of take surfaces that realize them. We lift these to the universal cover, and kind of they have these kind of limit sets in the boundary infinity when we lift them to the universal cover. Right, this like kind of squiggly curve I drew is like bounding the surface that we lifted. And we can kind of measure how far away like the surface is from being totally geodesic sort of by how close this kind of squiggly Jordan curve that I drew at infinity is from being a round circle. And how close it is measured by how close this like big K is. It's always bigger than or equal to 1, but if it's close to 1, then that means that you're close to being a round circle. All right, so those are most of the definitions. So right, to get into stating the Caligari-Marcus-Neves theorem, what I want to do is define these sets S epsilon of M, which are going to be homotopy classes of just immersed surfaces whose fundamental groups injectively include to M, but whose limit sets are 1 plus epsilon quasi-circles. So, I mean, we require like this big K for which their limit sets are K quasi-conformal homeomorphisms or deformations of the equator. We require that to be less than or equal to 1 plus epsilon. So I mean, this condition is just it's saying the limit sets are close to being round circles, and we only look at the surface subgroups whose limit sets are close to being round circles, and for these S epsilon of M's. Right, and so Caligari-Marcus-Neves defined this like entropy functional, which is defined by the following formula, which I'll kind of explain here. So they're going to do is they're going to, send epsilon to 0 and take a lim inf of the quantity that is this fraction here, as L goes to infinity. So right, so what does this mean? So so the entropy functional, it's defined on metric. So it just takes some metric G on your manifold M. So not necessarily the hyperbolic one, but just any metric. And what this kind of area sub G means is of like an element of S epsilon of M. Right. So what's the area of a homotopy class of just of like some pi1 injective immersed surface is just, you just take the smallest area over all surfaces that are in that homotopy class, which by what I kind of explained in the previous slide, you can realize this area by an immersed minimal surface. Okay. So really this is kind of like a count of
and if G is not hyperbolic, but is close to be hyperbolic, you can also do this construction of a minimal surface that minimizes the area among the homotopy class.
Yeah. So that's true in any Riemannian three manifold. Yeah, you can just do that. Yeah, so that's I guess I said on the previous page for.
Don't you need negative curvature?
No, I mean, you might have multiple. Yes, you don't know it's unique, but if you just want to get at least one, you don't need negative curvature. The like Shane-Yao, Sachs-Lundberg stuff doesn't.
Yeah. Okay. I see.
Yeah.
Right.
Okay. Thank you.
Thanks, yeah. Yes, you can have like multiple of them that minimize area. But yeah, that's why it's only kind of like semi-canonical. But yeah, if you just kind of just choose one of them, I guess, then yeah, then you'll just have one. So yeah, so that's what this area of a homotopy class means. It's just kind of the infimal area over all the surfaces in the homotopy class, which is realized by a minimal surface. And so what you do is you kind of the work that Kahn Markovich did, it's going to tell you that this quantity is going to grow exponentially as you send L to infinity, exponentially in L, basically. And so yeah, so you just kind of take a log of it and divide by kind of a normalizing factor, and then you can just kind of get a number out of this. That's sort of like a renormalized count of like how many minimal surfaces that you have with small.
Is there some kind of idea of why it's some L log L that you are looking and not L like you do in entropy for the geodesics?
Yeah, right. It is different from what you have for geodesics. Yeah, that's just Kahn Markovich did this count. Yeah, I haven't looked at that paper in a while, but yeah, I guess it's kind of the rate of mixing you have for the frame flow, I think, goes into that. And yeah, I don't have like a good, I guess it's kind of growing faster than what you have for geodesics.
I think L log
it's
L,
interesting.
I think L log L usually means you have a gamma function kicking around in there somewhere by Stirling's formula.
Yeah, there's like a factorial or something, if I remember. Yeah.
Amina. Okay.
Cool. Yeah, it's yeah, you basically like these surfaces are kind of like you have all these like pants, kind of produce great abundance of pants sitting around in the surface using kind of mixing for the frame flow. You can glue them all together in a way that you get a pi1 injective surface, and then there's just lots of possibilities, I guess, more than you have for geodesics. So yeah,
just have a question just to understand the quasi-conformal factor. I'm wondering if you start with the surface subgroup, and in this surface subgroup, you take other surface subgroups of finite index, and then you can take an immersed minimal surface realizing these finite index surface subgroups. And I'm wondering what the quasi-conformal factor is. Does it go to 1? What, you know, when the finite index is going to infinity, you know. Like the index.
No, it's a good question. So you get, I think you'll have the same quasi-conformal constant. Okay. So what's kind of maybe hidden in this is that I just said conjugacy classes. I didn't say commensurability classes or anything. So I mean, in this entropy functional, you're going to be like seeing kind of covers of things.
Yeah.
You can take covers. So you just kind of you have some kind of like multiplicity when you're taking all these covers, and that's just kind of like.
Yeah, and what's the effect on the quasi-conformal factor? Does it get better? Does it get closer to 1?
No, if you just take covers, it stays the same.
It'd be just the same. Okay, all right.
Yeah. But so then, you still have these covers inside. Like it's so quantic combos. You can define a similar functional if you like kind of just took one in each commensurability class. Caligari, Marcus Neves don't do that in their paper, but I also think that'd be an interesting thing to look at. But yeah, they don't.
Yeah,
so
I think I get it now. It remains the same. Yeah.
Thanks, guys. It's
all right. Thank you.
Thank you. So there's kind of some multiplicity here, I guess, since you have covers in some sense. But so you can define this functional, and as people kind of pointed out, it's analogous to a similar kind of quantity that you could define just for geodesics in like a negatively curved closed Riemannian manifold, where, I mean, you could just look at how many different geodesics there are that are length less than or equal to L, like send L to infinity and like take the logarithm, divide by whatever, and then you can just kind of get a number out of that. And I guess it relates to the entropy of the geodesic flow. And I guess there's sort of a class of kind of inequalities that basically tell you that if there's like a locally symmetric metric or something, then that'll kind of be the metric that extremizes these sort of like asymptotic counts of geodesics subject to curvature conditions on the Riemannian metrics that you're looking at. So maybe Besson-Courtois, Lowe, and Hamstadt, those are some of the names associated with those theorems. But I mean, kind of the idea here is just to ask whether there's like a similar kind of thing for these Kahn-Markovich minimal surfaces that you could prove. So the theorem by Danny Caligari, my advisor Fernando Cotamarquez, and Andre Neves is that there is a theorem like this. So if you just assume that the sectional curvature of metric G that you're looking at is less than or equal to -1, then first you have that the entropy they define is bigger than or equal to that of the hyperbolic metric. Okay. Why does that make sense? I mean, if you have the sectional curvatures being less than or equal to -1, that should mean you're sort of like more scrunched up than the hyperbolic metric, right? So you're kind of like smaller, and if you're smaller, there should be sort of more small minimal surfaces, and so your counts for how many minimal surfaces there are with like area less than or equal to something will be bigger, and so that's why that sort of makes sense. And they also prove like kind of rigidity in the case of equality, so that if you actually realize equality in this inequality for the entropy, then you have to be isometric to the hyperbolic metric. I'll just like, I don't really have time to talk about how this is really proved, but I'll just say that the proof of the equality in the case of rigidity case, it uses the Radner-Shaw theorem, and it's kind of based on a pretty creative application of that. That's like the theorem that's kind of the starting point for my work. So this is just, you kind of define this entropy functional analogy to what happens for geodesics, and here you're able to prove a theorem, and the analogy kind of works out. So you can ask whether, other things that are true for geodesics are also true for these the minimal surfaces that correspond to these S epsilon events. right? And so one question along those lines is that Andre Neves asked in one of his talks is whether for these negatively curved G that you're looking at in the previous theorem and the kind of immersed minimal surfaces that you're counting in that theorem, you can ask like whether these are dense in M, dense in Gaussian bundle of tangent two plane stem. In kind of, I mean, analogy to the case of geodesics where closed geodesics and negative curvature are of course going to be dense. So yeah, I was able to give a partial answer to this question. So there's an affirmative answer if G is in this some neighborhood of the hyperbolic metric to which the theorem I'm going to say in the next page applies. So basically it's kind of like reasonably sized neighborhood of the hyperbolic metric. I'll say more in a second about, yeah, that neighborhood. But I guess I'll also kind of say more in this in a second, but it seems possible that this question has a negative answer for some negatively curved metrics G. And yeah, I'll also say more about that. But okay, just to get in the main theorem for this talk that I approved. So the setup is we're just going to be looking at a just smooth one parameter family of negatively curved metrics on M that starts at the hyperbolic metric. Okay. Then what the theorem says is that, I mean, we can match this one parameter family of negatively curved metrics by a one parameter family of foliations, which we'll call F sub t, of the Gaussian bundle of tangent two planes for all t kind of contained in this maximal time interval from like 0 to big T. So big T is sort of the maximum time we're able to do this. Such that, right, so the foliations that we're constructing, they're going to start off at this like model foliation blue F that I talked about at the start of the talk. And instead of the leaves of each F sub t, like instead of kind of coming from lifting totally geodesic surfaces inside M to the Gaussian bundle of tangent two planes, they're going to come from lifting minimal surfaces in M to the Gaussian bundle of tangent two planes. Right, so we're going to have these minimal planes that we construct inside M, and each point take their tangent plane at that point, and then we lift that to GR2M, and that'll give us some surface in GR2M, and all these surfaces that we construct are going to piece together to form a foliation of GR2M. And the third condition is that these foliations that we construct are conjugate to the foliation blue F by these maps V sub t that are gonna just be self-homeomorphisms of the Grassmannian, or GR2 or self-homeomorphisms of GR2 of M. And right, I mean, these are just gonna be mapping leaves of the start foliation blue F to leaves of F sub t. So so basically these homeomorphisms just conjugate the foliation blue F to the foliations that we construct, sending leaves to leaves. Cool. So that's the statement of the theorem pretty much. But yeah, I mean, kind of the big question is like, what happens when you can't construct these foliations? So there's this large T here, and if big T is bigger than 1, then you can do it on the whole interval. But if T is less than or equal to 1, then something bad happens. So the failure clause for this theorem is the following. So if big T is less than or equal to 1 and we can't construct the foliations on the whole time interval, then what has to be happening is there's sometimes T sub n that are going to big T, and sequence of immersed minimal planes S sub n that are minimal for the metrics G sub Tn on M, that basically like lift to leaves of F sub T sub n, so that this quantity asterisk below is kind of going to 0 from below as n goes to infinity. So as these times T sub n are approaching big T. Right. So what is this quantity? So the first term here is so we have a sub s sub n of xn. So we have the sequence of points x sub n that are just contained in Sn. And what a sub Sn of xn is just like the second fundamental form of Sn s sub n at x sub n. Okay. And then we're just taking the norm of it squared. So another way to say what this term is just it's the sum of the squares of the principal curvatures of S sub n at x sub n. Yeah, and so that's the first term, and the second term is just the Ricci curvature in the metric G sub n, just in the normal direction. So we have nu sub n are the unit normal vectors to S sub n at x sub n, and yeah, and that's sort of the like ambient curvature term. Right. So what does this like asterisk condition kind of mean? So maybe the first thing to think about is what this ends up being for kind of, the foliation blue F is, in that case, we're looking at, totally geodesic planes inside it's like our hyperbolic through manifold. And so since like our surfaces are totally geodesic, then the second fundamental form will vanish. So the first part of this asterisk quantity is just going to be 0 in that case. And so we'll just be left with the Ricci curvature of our hyperbolic manifold in the normal direction. So it'll just be -2 everywhere. So starting out, this asterisk quantity is basically -2 everywhere on like all of our leaves. And as we vary the metric, it potentially gets closer and closer to 0, and that's sort of when our construction fails. But as long as kind of this asterisk condition is true on all of our leaves, then all the points in all of our leaves, then we're sort of in good shape and can construct these minimal foliations that are kind of deformations of the constant curvature, like totally geodesic blue F foliation. All right, so yeah, so some remarks on this. So it's like case of like big T being less than or equal to 1 when we can't actually construct foliations over the whole interval. What is kind of happening there is that, yeah, as I kind of indicated in red on the previous page, is the leaf curvatures, or kind of the principal curvatures of the leaves, are sort of failing to be bounded by the ambient curvatures. So yeah, so that's kind of the thing that can go wrong. Yeah, question that probably occurred to people when I said this theorem. So there are, of course, examples of negatively curved metrics to which this theorem can apply to produce a foliation like this. So this is like just only some neighborhood of the constant curvature metric. And so the examples that I construct in my paper of kind of metrics to which this theorem can apply are kind of hacked together. Like I can't do it for every closed hyperbolic through manifold. I have to pass to a lot of finite covers, and it's there's probably a better way to do it than kind of the approach that I had. But there certainly are negatively curved metrics on closed hyperbolic through manifolds to which there are foliations like I said in the theorem. I should also say that so for number 2, these examples of negatively curved metrics to which this theorem doesn't apply are those are sort of examples I was referring to when I said that density for the minimal surfaces that you consider in like the Caligari-Marcus-Neves theorem might fail for a certain metric. So it's these ones I think they might fail for, but density might fail for us, but I don't actually know how to prove that. But another comment on this is, so yeah, it's kind of builds on work that Gromov did. So he has a paper where he constructs foliations like kind of the ones I construct in my theorem, or but he does it in all dimensions. So it's kind of a more abstract, more general kind of a approach that he has. And the leaves of the kind of foliations that he constructs are close to being totally geodesic. So what that means here is, I mean, we have this quantity, this like asterisk quantity, and for the foliations that kind of Gromov constructs, like this quantity always remains close to -2, right? So the second fundamental form is very small, and the Ricci curvature is kind of stays close to -2, since you're sort of looking at small deformations of the constant curvature metric. And yeah, I guess I would say that like kind of my work sort of grew out of trying to understand or find a simpler proof of what Gromov did in the case of dimension 3. And so, yeah, I guess in dimension 3, you can kind of get a larger neighborhood of the constant negative curvature hyperbolic metric, for which you have these foliations. But yeah, the thing that Gromov does, it works in all dimensions. Yeah, and then I'll also just mention that probably, I mean, dimension 3 isn't that important here. You can probably prove like a version of the theorem that I just said in higher dimension and codimension. Like there's kind of one part in my proof where I really use dimension 3. So the result in higher dimensions would probably be slightly weaker. Like you maybe wouldn't know that the surfaces that you construct piece together to form a foliation, but you'd still be able to kind of construct them. We're not going to say too much about that, but so what would you be kind of, what would the higher dimensional examples be? What would the model cases be? So, I mean, if you just have a hyperbolic n manifold, then you can look at the Grassmann bundle of tangent k planes to it in the same way as we've been looking at GR2 of M for this whole talk. And this will also have just kind of a natural totally geodesic foliation just by it's like immerse k-dimensional totally geodesic planes and lifting those by their tangent planes, right? And the sort of theorem that I guess I haven't actually written this down, but I'm kind of 99% on this, is if you just take one parameter family of metrics, just starting at the hyperbolic metric, like in the theorem that I just said, then what you should be able to do is basically construct foliations of GRK of M, like in the theorem, and then it'll sort of work until the leaf curvatures get bigger than the ambient curvatures. And so like in higher dimension, higher codimension, it's maybe a more complicated expression that you would write down, but it's basically kind of of the form, the leaf curvatures have to be kind of bounded above by the ambient curvatures. And then as long as you have that, you should be in good shape. Okay. So right. So that's the kind of the main theorem. Can get to say a couple words on how you prove it. Right. So what does this like asterisk condition mean? It basically just is telling you that how you use it is it lets you produce a mean convex foliation of kind of small neighborhoods of the sigma sub t. Yeah, just kind of if you flow outward just by look at like the parallel distance S surfaces to it, then what this term here being less than 0 will tell you is that since we're negative curvature and so forth, and it'll tell you that kind of your small tubular neighborhoods are going to be mean convex. So just I'll just kind of say briefly kind of how this all works. So we follow the approach of Anderson to solving the asymptotic plateau problem. So what we do is we lift everything to the universal cover, right? So we have some surface sigma sub t, like in one of the foliations where we're assuming we're good up to time t, right? So this is sort of like a method of continuity argument a little bit. And right, so we lift our surface sigma sub t to the universal cover. We get this like surface here, sigma sub t tilde, okay? And it has, if we look at like the parallel surfaces that are at distance like plus epsilon and minus epsilon to sigma sub t tilde, which I've drawn here as these surfaces kind of above and below sigma sub t tilde, and the arrows outward indicate that these surfaces are mean convex. And so what happens is if we just vary the metric a little bit to g sub t plus epsilon tilde, then what we're going to do is we're going to then these like mean convex surfaces that were mean convex in g sub t tilde that I've drawn here with arrows pointing outwards from them, those are going to remain mean convex if we just kind of deform the metric a little bit, right? So if we're strictly mean convex, that's stable under small perturbations of the metric. And so kind of what we're going to do here is we're going to measure circles in sigma sub t tilde, kind of going off to infinity. And for each of these circles, we're going to solve the plateau problem, right? And can sort of define minimal disks that bound these circles, and passing to a subsequential limit, sending the circles to infinity, we get the surface sigma sub t plus epsilon tilde that I have drawn in blue. That is kind of a minimal surface for this new metric, g sub t plus epsilon tilde on the universal cover. And so this construction of these surfaces, like the blue sigma sub t plus epsilon tilde, is going to be equivariant for the action of the fundamental group of M on the universal cover of M. And so basically this whole thing is going to descend to M, and we're going to get like a foliation of GR2 of M. And yeah, so there's a lot of details in this I'm not saying, but I would say probably the key thing that you kind of have to worry about is the possibility that uniqueness to like these asymptotic plateau problems is failing. So like, what if there's some surface that I'm drawing it's kind of like a dotted blue surface that stays at finite distance from sigma sub t tilde, but is not contained in this small mean convex neighborhood that I drew. And so what that would sort of do is it would lead to kind of gaps in the foliations that we're trying to construct. Right, and so yeah, I mean, the key point here is that as these surfaces sigma sub t tilde vary, we want the blue surfaces to vary continuously, okay? And so if uniqueness fails and there kind of isn't a canonical blue surface, and and that'll basically kind of, I mean, that'll break our foliation. So in order for, I mean, kind of the surface that we construct, in order for them to vary continuously in the sigma sub t tilde, then really the condition that we want is sort of a like uniqueness for the relevant asymptotic plateau problem here. So yeah, that's kind of a really brief sketch of.
So sorry, can you explain? I don't know if I understood well why the uniqueness rules out the gaps of the foliation. What do you mean by that? That if you don't have the uniqueness, you can have a.
Yeah. Say a little more on that. So, I mean, I did this like kind of whole thing for a single sigma sub t tilde, right? And so I can do this for other sigma sub t tildes, right? Other ones that lift to things like this, and that are just draw them in red, say, and that are sort of approaching our sigma sub t tilde, right? Just call them sigma sub t tilde prime, okay? And what we want to happen is, I mean, for each of these sigma sub t tilde prime that I drew, I mean, you have some other blue surface that's a minimal surface and kind of the perturbed metric that you're just trying to go a little further and construct the foliations for. And if these blue surfaces, if they're all sort of, if as sigma sub t tilde approached, as this like red surface, as these red surfaces are sort of approaching sigma sub t tilde, if the blue surfaces that you constructed for them that are kind of these minimal surfaces in like the slightly perturbed metric, if these are not, if the minimal surfaces that you construct are not converging to the sigma sub t tilde, then you get another one. And yeah, so that's kind of how uniqueness fails.
Very nice. I liked it. Okay.
Yeah, thanks. Yeah, thanks for clarifying that. Yeah, that's kind of the main point. There's a lot of things you have to check, but that's really the main thing to worry about. Yeah, I'll just say briefly, this is inspired by Karen Uhlenbeck's work on minimal surfaces and quasi-Fuchsian manifolds. There's sort of a specific regime called, I guess the almost Fuchsian manifolds. So what these look like is, I mean, it's a high constant curvature -1 hyperbolic metric on sigma times r. Okay, and so it'll be kind of skinny in the middle, but it'll flare out at the ends. And what you have in this kind of specific regime is you have like a unique minimal surface in the middle. Okay, and the principal curvatures of this minimal surface are less than 1 in absolute value. That's kind of the condition you put on this. And why less than 1? Because I mean, the curvature of hyperbolic space is -1, so this says the principal curvatures are kind of smaller than the ambient curvatures. And so what this lets you do is it gives you it's like mean convex. If you just kind of flow out normally, you get these like mean convex, this mean convex foliation by parallel surfaces. Okay, so it lets you rule out the existence of other minimal surfaces, and basically you're able to parameterize kind of the whole space of hyperbolic structures on sigma times r in this like specific regime where you have like a minimal surface in the middle with small principal curvatures, but you're able to parameterize, you're able to recover the whole hyperbolic metric by just the conformal class of the induced metric on the minimal surface in the middle and its second fundamental form. And so this kind of gives you another way of parameterizing like quasi-Fuchsian space and kind of a neighborhood of sort of the Fuchsian locus. So kind of this condition where you have kind of your principal curvatures being bounded above by the ambient curvature. So like in this asterisk condition, it's kind of not exactly that, but it's in the spirit of that, where if you have that condition, then you have like a small neighborhood at least where you have a mean convex foliation, and then you're in good shape. Okay, so I can get to some of the applications. I'll just try to go through these really quick. So if we have a sequence of these surface subgroups, their limit sets are approaching some circle in the boundary infinity, right? So these Jordan curves, and they're getting closer and closer to being actual round circles, and they're approaching this round circle, which I'll call C, which we think of as the boundary infinity of a totally geodesic plane. So basically we have a sequence of surface subgroups that are kind of getting more and more totally geodesic. The fact that like the quasi-circle limit sets approaching a round circle means that the surfaces themselves, the principal curvatures are going to 0. Like that fact is due to Andrea Seppi and is important in my paper, and is also important in the Caligari Marcus Neves paper. So then, okay, so take a metric on M where we have a foliation from our main theorem. Then there's sort of a density theorem that, these surfaces S sub n that are minimal surfaces in the metric G are going to be, this sequence of them is going to be dense. So for any tangent 2 plane, we can find like, we go far enough out in the sequence, our surfaces will all have tangent 2 planes that are close to that. So that's kind of a density result. You can make this quantitative under an assumption on the closed hyperbolic 3 manifold that probably isn't necessary. So I won't say about that, but then we have this, can also prove this quantitative version for totally geodesic surfaces, right? So if we have a closed, I'll just kind of skip to the totally geodesic theorem and say this really quick. So if we have infinitely many closed immersed totally geodesic surfaces in the hyperbolic metrics, so that happens in a lot of the arithmetic cases that you look at, hyperbolic 3 manifolds arithmetic. And if you let sigma sub n prime be the corresponding minimal surfaces in like M in this metric G, okay? Right, so the sigma sub n are like closed leaves of the foliation blue F, and these sigma sub n prime are in the same homotopy class as the sigma sub n. So they're gonna be like closed leaves of the foliations that we construct. And the statement is that if you just kind of take the probability measures that correspond to these sigma sub n prime and look at all the weak star limits, then these have to have full support in any weak star limit of the sequence of probability measures has to have full support in GR2M. So it has to assign positive measure to every open set. So not only are these surfaces kind of dense, they're also spending a decent amount of time everywhere. And yeah, so then quick word in the proof, and I'll be done, is the constant curvature input is that we know that the sigma sub n are equidisputing by this like Moses and Shaw result from the 90s. So that's constant curvature, we're good. And then we basically use the conjugating map phi from the theorem to transfer this information to the variable negatively curved setting. We lose a lot of information, but we're still able to say weak star limits assign positive measure to every open set. And that's sort of using the kind of techniques from the Caligari Marcus Neves paper to do this. But yeah, and I guess I had some kind of questions about like these weak star limits of these sigma sub n prime and regularity of the conjugating maps phi in the directions transverse to leaves. It's like how they're continuous, like for the case of geodesic flow. But yeah, that's, I guess it's 9 now, so I should probably but yeah, I guess I'll end my talk here. But
Ben, there were quite a lot of questions, so I don't think anybody will mind if you talk for another 5 more minutes, if that's okay with you.
Oh, cool. Yeah, I can. Yeah, thanks. Yeah, I'll just if you're good with it, yeah, I'll just.
Yeah, please.
Cool. Yeah. Awesome. Yeah. I'll just say kind of a couple words on some questions that I don't know how to do in possible future directions. So, right. So we have these surfaces sigma sub n prime from the theorem, this totally geodesic theorem that I just said, that are kind of the minimal surfaces in the variably negatively curved metrics that correspond to the homotopy classes of surfaces that are totally geodesic in the constant curvature metric. And the last theorem I said was that these weak star limits have full support, or weak star limits of all weak star limits of the sigma sub n prime have full support in Gaussian bundle of tangent 2 planes. So one question that you could ask is, I mean, in the constant curvature case, the only weak star limit is just uniform measure from the Moses and Shaw result. So you have homogeneous dynamics there and you get that. But yeah, you can ask like what possible weak star limits you can get. Is there only one? I mean, or can you get lots of them? I mean, probably any weak star limit you get in variable negative curvature has to be like singular with respect to Lebesgue measure and is like really bad. But if there's anything you can say there. Another question you can ask is, I mean, you have these conjugating maps phi from the theorem that send leaves of kind of the foliation blue F to leaves of the variable negative curvature foliations that you construct. And along the leaves, these maps should be smooth, but probably in directions transverse to the leaves, the regularity will be worse. You have sort of a similar thing for if you have a hyperbolic manifold and you look at another negatively curved metric on it and you look at the two geodesic flows, and you have a similar kind of conjugating map that will send orbits of the geodesic flow in the constant curvature one to orbits of the geodesic flow in the variable negative curvature one that's mapping the unitangent bundle of one to the unitangent bundle of the other. And in that case, the regularity in the transverse directions is like at best Helder, like it's not differentiable in the transverse directions. And so probably something like that is true here, I would guess, but I don't really have any idea how to do that. And yeah, at least as far as kind of the dynamics of foliations with negatively curved leaves go, I think I'm very much an amateur to kind of that stuff, but one way that people study that is they look at the foliated geodesic flow in the tangent bundle of F, the foliation. So just kind of looking at geodesic tangent to leaves. And in our case for the foliation blue F, this would just be like the diagonal action on the frame bundle of our manifold, which is just PSO2C mod pi 1 of m. And so that'll end up being the foliated geodesic flow in the constant curvature case, but of course the variable native curvature case, I mean, it's not like an algebraic description, but and so yeah, so there are kind of lots of measures that are natural to the foliated geodesic flow, like harmonic measures, which are kind of like taking Brownian motions along the leaves. And you can look at the limits of large metric balls. And so, I mean, what you can ask is whether there's any kind of measure classification in this setting like you'd have in the constant curvature setting, or if you could prove some negative result, like bad things happen, like you can get kind of all kinds of measures. And I mean, you can also ask just for statements that say that the bad things happen when you're in like kind of variable negative curvature, and then when you're in constant negative curvature, of course, you know, kind of by Radner's theorems and homogeneous dynamics, that you should be okay. Yeah, and I would say that, yeah, Sebastian Alvarez has like kind of some results where he looks at negatively curved metrics in kind of a different context, but is able to kind of like prove some of the things that I said in sort of his setting. So that's a little bit encouraging, I think, for like the prospect of answering this question. But yeah, I don't really have any idea how to proceed. And one final thing I'll say is that another line of questions that you can ask is in the almost Fuchsian case, there's sort of a really rich theory where like all the different measures of complexity of a quasi-Fuchsian manifold in the almost Fuchsian case. So you can look at principal curvatures of the minimal surface in the middle. You can look at the volume of the convex core. You can look at the Hausdorff dimension of the limit set and the quasi-conformal constant for the quasi-circle for the limit set. And there are all these theorems that relate these different measures of complexity in kind of the almost Fuchsian regime of quasi-Fuchsian space. And so for the kind of setting here, I think you could ask similar questions. You ask for theorems that relate, I don't know, how far away the metric you're looking at is from the constant curvature one. You can look at like how big the principal curvatures are of the minimal surfaces and like these foliations that are constructed in the main theorem. You can look at if you lift the minimal surfaces of the universal cover, like their limit sets in the boundary infinity should have Hausdorff dimension bigger than 1. You can look at that. So there might be kind of a similar kind of line of inquiry for these foliations that I constructed. But yeah, so that's all I'll say. But yeah, thanks for the opportunity to speak and for listening to my talk.
Thank you very much, Ben. So everybody, yes, please unmute your speakers. And excellent. Thank you very much, Ben. Are there any questions, please?
I don't know. Questions, I have 1,000.
Go for it,
you
Sebastian.
Open the door.
Go for it, Sebastian.
It's a very nice talk, very exciting results, and you open the door, so you have like 1,000 questions natural that appear. Very nice. So I don't know. For example, you have this entropy that you define. If you look at the case of the geodesic flow, the analog, which is the volume entropy, is also the topological entropy of the geodesic flow. Do you have thought, or maybe something like, if you look at the foliation that you have and you try to look at the topological entropy, there is a notion of topological entropy for foliation, which is due to Gis, Langevin, and Valjac. if there's some kind of relation between your kind of volume entropy that you have in this topological information. This is a kind of a very natural question that you
Yeah, yeah, yeah. I didn't really know about. Yeah, that's really interesting. Yeah, I didn't really know about topological entropy for affiliations, but yeah, that's I wonder if there is. Yeah, that'd be interesting to look at.
Okay. No, I don't expect an. I mean, I just tell you that actually, for me, this is very nice because you have lots of directions to go. I mean, it's beautiful.
You said Geese and
Gis, Langevin, and Valjac. So it's a work from the 83, I think. 88. Well, end of the 80s. So they define what you do. You have a foliation. You look at how leaves separate. And how do you do this? You draw some path in the leaves, and you see the holonomy along this path, and you count how many paths you have that separate leaves. And this gives you a notion of topological entropy, which coincides with the topological entropy of a flow when your foliation is of dimension 1. And you also see if this entropy is 0, it means that you have a transverse measure invariant, which is not your case, if I understood well. And you could have, but it's also interesting to understand how it is. But I suspect that in your case, you should have some interesting dynamics, and that it could be an interesting stuff to study. This would be for the topological side.
I see. Yeah,
now, from the dynamical side, you have all these discussions about which star limit appear as a. Okay. In your case, it's very interesting. In particular, the harmonic measures, you don't need any assumption of the curvature to define them. You have a Brownian motion, and you look at what happens. So this is very natural. And then the result that you quote of me, actually, I have absolutely no generalization in sight of.
Oh, okay.
I don't know, even if, for example, if I have a Schottky holonomy, I don't know how to do. I've been spending some time after my thesis, but I did not do nothing. But it's interesting. Maybe in your case,
okay.
These foliations are all of conformally hyperbolic type, which is interesting.
Yeah. Right. Yeah.
So I won't take more time to ask you more questions. But if you want some, I can write you, or maybe sometime. I don't know if you know South America, but you could visit.
Yeah, no,
it's a nice place to go mathematics. It's a nice place to go.
Montevideo is a beautiful city.
Montevideo is nice.
Yes. Notwithstanding Sebastian.
I'm going to write you because it's. I was very, very interested by the talk. I think it's very natural what you do.
Thanks. Yeah, we should talk more.
I also have a question.
By all means, Andrea.
Yeah, so great talk, Ben. I have a question about you have this argument to infer. Let me put it here. You have this argument to infer from the uniqueness or the asymptotic Pareto problem. You infer the fact that foliation has no gaps. You explained this argument more or less. But are you using some sort of compactness for minimal disks with asymptotic boundary in negative curvature for this argument? It's a little technical question, sorry. But
yeah, so the kinds of compactness results that we use on the paper, it's I guess sort of the surfaces that you're looking at, they're all kind of like graphical over the blue surfaces. If you remember my diagram, they're sort of like graphs over the last surface that you constructed. So really kind of as long as you have like control in the second fundamental form, you're sort of okay for taking limits. So yeah, I guess I would say, yeah, for the kind of the compactness sorts of results that, but yeah, the compactness arguments are kind of simplified, I would say, by the fact that, yeah, your kind of surfaces that you're constructing are like locally graphical, and there's some like kind of work to set everything up, definitely. But yeah, I would say that kind of makes it so it made so that I didn't have to think that hard about the compactness.
I guess this is the kind of compactness that you also need to prove the existence for the asymptotic plateau problem, I guess. I don't know.
Yeah, I mean, yeah, I guess, yeah, I think it's basically kind of like Anderson's argument. I guess I don't have to use like any GMT or like the variable compactness at all. Although if I did this for higher dimensions, I might. I think the fact, I mean, we have these like local mean convex foliations, so that really like the kind of solving the asymptotic plateau problem. I think it's a simpler argument than like even just like Anderson's paper. I think it's, yeah, that really makes it a lot easier, I would say. So
But Anderson,
the kind of analysis that goes into that, it's not really that hard.
but doesn't Anderson just apply GMT? He builds convex sets in hyperbolic space and then applies GMT. Isn't that right?
Yeah, that's kind of how his approach goes, where he just kind of takes the disk going off to infinity and then uses the GMT compactness theorem, and there's like a hyperbolic space monotonicity formula that he needs to like prevent things from like leaving kind of like the convex balls in the middle.
Mm-hmm.
But yeah, I think the stuff that since for my paper, it kind of after the kind of convexity fails, like after the leaf curvatures kind of fail to be bounded by the ambient curvatures, then the uniqueness fails it. But as long as you're kind of in that like kind of with that assumption, then it makes some of that a bit easier, I would say.
Are there any other questions, Andrea?
No, it's good. Thanks.
Okay. Anyone else got any questions? I'd like to ask a question. If you take a hyperbolic manifold and you take its totally geodesics, then that gives you a foliation of the Grassmannian bundle. If instead of totally geodesics, you take equidistance, then that gives you foliations by surfaces of constant intrinsic curvature, doesn't it?
Yeah.
So do you think you could do the same thing for surfaces of constant extrinsic curvature?
Yeah. So actually, that's a good question. I thought briefly about that. I think it will work. I think, yeah.
My experience is these things are nicer than minimal surfaces. They behave better.
Yeah, I think so. You want as long as you're able to kind of get like sort of a local foliation where the mean convexity is bigger, it's more mean. The mean curvature is bigger on one side and smaller than the other side.
Yeah.
So for example, so you want, I think, the curvatures to be bounded by the ambient curvature, since for like horospheres, say, this won't work.
Indeed.
Because like then the equidistant surfaces are themselves horospheres. So
Indeed.
But yeah, it should work from the setting that you described. Yeah, equidistant surfaces. I think it should basically go through.
Actually, François Laberry has some very interesting work about constructing laminations of manifolds by constant curvature surfaces. I know that Jeremy is here, and he's worked on very similar stuff. So perhaps these results might be of use to you. The one thing I can say about constant extrinsic curvature surfaces in constant extrinsic curvature surfaces is that the compactness results that you have at your disposal are much nicer, much friendlier than the compactness results that you have at your disposal when you're studying minimal surfaces. So that might help you.
Oh yeah.
Have you thought of looking at this problem in terms of holomorphic foliations of contact manifolds? Because ultimately it comes down to that, doesn't it? Your Grassmannian is a contact manifold. These foliations are holomorphic upstairs in the Grassmannian, unless I'm mistaken.
Yeah, that's a good. I haven't really, but yeah, I think this would kind of. I mean, as long as you kind of have like a model case where you have that the principal curvatures are sort of smaller than the ambient curvatures, as long as you sort of had that, then I think you'd be in good shape for doing something like this.
Because
Yeah,
maybe perhaps the space downstairs, the metric downstairs, is a bit of a red herring, possibly.
Oh, what did you say?
Maybe the metric downstairs is a bit of a red herring, and what is happening is actually upstairs. You see.
Yeah, right.
The Grassmannian bundle.
Yeah, I guess. Yeah, you could look at yeah, the metric there and try to that's a good point.
Okay. Finally, I mean, given that I'm here, I'll just ask one more question. Do you know of any? Have you thought of maybe there might be some sort of Colding Minkowski type compactness result for these foliations?
Oh, yeah. Okay, so I'm not that familiar with the Colding. Yeah, they have like kind of this 3 dimensions, this like really rich.
Yes.
So yeah, one thing I would say, so kind of you don't know the foliations continue to exist once this sort of curvature condition fails to hold. So what you get is gaps in foliations.
So that was a question I had. So when you take a limit, in the limit thing, you can actually have gaps opening up spontaneously.
I think so. Yeah. How does it happen? Yeah, I haven't thought too much about how.
Right.
I think one thing that will happen is maybe gaps won't happen, but the surfaces will kind of, you'll have new surfaces from further away. Or but yeah, you should get. So maybe it'll go from like no gap to having like a definite gap. I think that will happen.
Right.
I haven't thought that much about this, but yeah, it'd be interesting. Like, I mean, if kind of when gaps form, like whether you can get, there should be only finitely many surfaces. You should get like some lamination. Really, you should get a lamination.
I wonder as well.
Yeah, I haven't.
Is the full? Do you think the foliation might stop being unique? Is the foliation unique, in fact?
Yeah. So it should be unique in the sense that, I mean, if you look at kind of other possible foliations where their leaves lift discs in the universal cover that are at finite distance from the one you started out with, and it'll be unique over all of those foliations. But
right.
Yeah, but then after at some point you have laminations, and then I don't really know what happens there. But
right.
Yeah, but what I wanted to say was like kind of the gaps in these laminations should force the kind of surfaces you're looking at that sort of limit to leaves of the foliation, like the these like Hahn-Markovich minimal surfaces. It should sort of control how those are distributed, but I wasn't really able to come up with a precise argument for that. And then you get some kind of density failure maybe, but yeah.
Okay. Well,
and do you can play with other surfaces than the one explicitly constructed by Kahn and Markovich? Oh, I don't know if it's clear what I'm saying.
What kind of surfaces?
You in your no, I will try to think again about my questions. I thought maybe some of the construction that you have depended on some construction of Kahn Markovich to construct pi one of surfaces inside pi one of a hyperbolic manifold. But I will think again of my question. I think it's not clear. Sorry.
Anyway, it's getting late now, so I think we can wrap up the questions. So let's just thank Ben once again for a lovely talk. So before I end the recording, I just want to make an announcement. So as we know, this is, as I said at the beginning of the talk, this is the last edition of the Pangolin Seminar before our summer recess, that is to say the Christmas recess. And so the Pangolin Seminar will return on Tuesdays again on the 26th of January, 2021. And the next speaker will be Jason Lowe from Oxford University. He hasn't yet announced the title, but I suspect it will be something to do with building Einstein manifolds using singular perturbation techniques. So once again, thank you, Ben, for the lovely talk, and I'm going to end the recording now.